like you have given the webinar,
Right.
including Somnath, lots of people. But what happens, once it happens, he get connected with them, continuously connected. That is his rare quality.
Correct.
So now when he went to London, he got many friends like Rakesh Kumar, and he has brought him here now.
Wow.
See?
Thank you, sir.
Fantastic.
Thank you, sir.
Fantastic.
How is Northeast these days?
It is good, sir. These days it is raining and sometimes it is very hot. So humid climate is prevailing, sir.
Okay. I have come there. We have got a Northeastern Center there. Long back, I visited all those places. I retired 20 years back from ISRO. So what I am telling is before
nice.
that.
Nice, sir. Nice. It's good, sir.
So time is already
Okay.
past 3.
Others, you can please start. You can begin. Okay.
Sure, sir.
These days are the time of examination for most of the school students.
Correct.
So
Yeah,
we find
correct,
it difficult.
Yeah, that's
Yeah,
true.
right,
For
That is
them
true.
to track them. But yet,
That's true.
we have got
Actually, sir,
25 plus today.
yes, sir. Actually, I shared this link with my astronomy club
Oh,
in my
good.
school.
Good.
But
Oh,
I
nice.
think only one or two have joined because since Monday their half yearly examination is going on, sir.
Oh, exactly. The same. Correct. Examination means there is more they are high priority
That's
area.
true.
They should be.
Correct.
Rightfully, it is a high priority thing.
Yes.
Okay. Others,
How
let's
is
start.
okay?
Okay. Please.
Good afternoon, everyone. I invite Rishika to the introduction. Rishika, are you there?
Am I audible?
Yes, you are.
You are.
Yes.
You are, Rishika. You are.
Okay. So, in the face of cosmos, the guardianship of Earth is no choice. It is our responsibility. Good afternoon, everyone. It is our privilege to welcome you all to the 82nd webinar session of the UL Space Club, an institution dedicated to fostering curiosity, inspiring scientific thinking, and building the next generation of space-minded scholars. Today, we gather under the guidance and support of some truly important pillars. First of all, Sri Ike Kuti sir, our founder and mentor. It is through his vision and unwavering commitment that UL Space Club has been able to bring us speakers of exceptional caliber. Adar Shetton, our webinar head. He is our driving force behind the design, logistics, and flow of today's webinar. And Sri Shajil UK sir, moderator, who will manage the proceedings and ensure our discussions run smoothly. We are deeply honored that Dr. Tarun Kumar Pant, Director of Space Physics Laboratory, VSSC, Thiruvananthapuram, has agreed to speak with us today. To say a few lines about Dr. Pant. Dr. Pant completed his PhD in physics after conducting doctoral research at the Physical Research Laboratory, Ahmedabad. He leads important work at SPL, including the optical and radio remote sensing of Earth's plasma and neutral atmosphere, studies of ionosphere, tomography over Indian longitudes, and investigations of Earth-Sun interaction and near-Earth space environment. We are extremely grateful to Sri Ike Kuti sir for arranging Dr. Pant to be with us today. Because of Sir's efforts in securing such a distinguished speaker, we have an extraordinary opportunity to deepen our understanding of phenomena that protect our Earth. Today's topic, Sun, Earth, and Guardians of Life, is profoundly significant. It is not merely about scientific curiosity, but about understanding the invisible forces and dynamics, solar radiation, magnetic fields, atmospheric layers, plasma interactions that make Earth habitable. It's about learning how the sun shapes life, how Earth system guard us, and how fragile and resilient that guardianship is. This topic connects our daily life with vast cosmos, from weather patterns and climate to technology in space to the survival of ecosystems. To all our students and participants, Please sit comfortably and ensure your devices are mute during the talk. Listen attentively, take notes, and reflect it on what is shared. If you have any questions, type them in the chat box during the presentation. We will have a dedicated Q&A session later on. We will try to cover as many questions as possible. This is a rare chance to interact with such a leading scientist, so make good use of it. Stay curious, engage fully, and let this session open new windows of understanding about our place in space and our responsibility as guardians of life. Thank you all. So now let us begin the session. Moving on to you, sir.
Okay, thank you.
Rishika, thank you very much. Thank you very much. I want just to tell Dr. Tarun Pant that she's not only good in explaining things and introducing things, she's also poetess. Poems she writes. So thank you, Rishika. Thank you.
It's my privilege, sir. Thank you.
Okay, thank you, Rishika. And it's a great pleasure to announce that it's a with the blessing of our founder, E.K. Kuti, former director ISRO. And today we have an exceptionally brilliant scientist from ISRO, Dr. Tarun Kumar Pant. He is talking on Sun, Earth, and its contributions of life, and it's somewhat about our existence on the Earth and something to be uncovered, things or enigmatic things of nature. We'll get some kind of ideas there. And he's an exceptionally brilliant scientist, and he is part of ISRO as the director of Space Physical Laboratory, and he's part of several Indian missions like Chandrayaan 3 and so many rabbit radio backend ionospheric tomography and LIVS HISIT and these kind of major program he headed, and he completed his MSc Physics in Government University Nainital and followed by PhD from Physical Research Laboratory PRL Ahmedabad before joining VSSC in 2001. He was at the University of Toronto, Canada as a postdoctoral fellow. He is the recipient of Best Thesis Gold Medal for his doctoral work at PRL, and he has recently received Hariom Ashram Pirit Vikram Sarabhai Award for Atmospheric Coupling Studies in 2015. He has been one of the 5 finalists of Indian National Science Academy Young Scientist Award for 2002. He is a reviewer of many international scientific journals and published more than 100 papers in high-impact, peer-reviewed international journals. Dr. Tarun has supervised and co-supervised doctoral works of 8 ISRO research scholars, and he is still continuing the research for our nation to lead the space power of this world. So we are proud as an Indian and part of this ISRO. We are proud of this great institute that lead the nation towards forward. And we are eagerly waiting for your word, sir. And I welcome all the teachers, students, and scientists who are gathered here, who are watching through online, through our YouTube channel, and welcome all to hear the interesting story of life and technology here. And I welcome Dr. Tarun to deliver his wonderful speech. Welcome, sir. Your mic is muted. Okay, sir, please. Please unmute your mic, sir. Okay. Sir,
Your mic is mute. Please unmute the mic.
Okay, sir.
Okay. Yes. I'm sorry. Yeah. Thank you, Professor Sajal. Thank you, Rishika. And I also want to thank Kuti sir for giving me this opportunity to be here on this session and share with you all the excitement and the work that we have been doing here. It will be like if through this talk, if I could enthuse a few students to think about the problems that we are trying to tackle here, I think that will be a great thing. So keep your interests alive, as Rishika was telling. And the talk that I have chosen today, the title, as you know, that it is Sun, Earth, and the Guardians of Life. So through this talk, basically, I wanted to explore that explore the question that not only we know that Earth is the only planet where life is possible as of now, even though we know there are many discoveries of exoplanets which are Earth-like planets and things like that where life is possible. But then as of now, we know that Earth is the only place which can give us some clue about how life came about, and then how it sustained, and what were the factors that were responsible for preserving it in the form that we see it today. So my talk would be a kind of a exploration of this story, and I'll try to sort of give you a glimpse of the things that we have done or the progress that have been done across the globe in this particular area. So I'll just share my present talk here. Just give me one.
Okay, it's visible, sir. Okay.
I'll go to the.
Okay, so please make it full screen. Okay, now
full
it's okay.
screen. Yes.
Yeah, okay. So,
yeah. So as I said, Sun, Earth, and the guardians of life. So I thought I will try to start from the very start, and that very start is the Big Bang, right? That is where, as we know today, everything started, right? So what you are seeing on your screen right now is the sort of a time evolution or cone of evolution of the matter and energy as we know today, which had come from the quantum fluctuation, which initiated the Big Bang, say somewhere around 13.7, 13.8 billion years. And we are now, through this understanding of this evolution of the cosmos, we know that how the stars are formed, how galaxies are formed, how the combination, the clusters, different clusters and different kinds of galactic systems are formed. And along with that, we also are forced to ask this question. The question is, are we alone in this whole universe as we see it today? And to answer this question, in the past, there have been missions like Voyager. We have tried to send missions like Cosmic Background Explorer. And then recently, the James Webb telescope has gone. That is the most recent and the latest in technology that is exploring the cosmic background. And you know that when we are looking at the cosmos, we try to look at it in more and more towards the infrared regions. I think most of the students know the reason. The reason is that the Doppler that we experience in the expanding universe, the more farther we go, deeper we go, we experience the deeper, the initial stages of the formation of the galaxy. So it will be all the more towards the IR or the far IR, near IR region of the spectra. So most recent telescopes, if you see, which are exploring this, they are exploring the cosmic background in near IR and IR region. On the right side, what you are seeing is, when we look at the sky, the night sky, we see many illuminated bodies in stars, right? And so this curiosity in earlier scientists, when they looked at this sky, they thought that can we relate, because all these stars have different luminosities or different light coming from them, their sizes are different, their distances are different. So can we put them in some sort of a uniform or a similar scale where we can understand one with respect to the other? And one such scale in astronomy, those students who are studying astronomy, they may be familiar, is called the Hertzsprung-Russell diagram. Okay, it is actually relating the temperature of a star, of a celestial body, with the luminosity that is being observed on Earth. So if you plot these together, what you will see is the kind of points you will see emerging on the screen will be something what we are seeing in this, right? You will see many points, and these many points will be following a particular slope or a particular band, which is green color here. And this band is called the main sequence stars, or the stars which are following this sort of a evolution. Means what? If we go to the right side, the x-axis, the right side, where the temperatures are close to 2300 of this order, from there the stars start evolving, and as it evolves, it brightens. So as it brightens, its temperature increases, and we see that its luminosity also increases, and it evolves in this. So in this, there are many stars in different stages of their evolution. And if we look at our sun comes where this red cross you are seeing. This is our sun here. As you can see, its surface temperature, the color temperature is somewhere close to 5000 degrees. And its luminosity is the standard one here. With respect to that, we can scale everything up in the sky, right? And the question, so naturally, when the sun will start evolving, it will still evolve further. It may follow this main sequence up. Its luminosity may increase, its core temperature may increase, and then it may follow, it may become a red giant, or it may follow a different path of evolution. But then one very interesting thing about these evolving stars is that these stars, when they are evolving, the basic source of energy, as we know, is the synthesis of elements that is happening inside their core, right? People know that, we know on that anything that we see, any element that we see on Earth is actually a stellar material, right? It has actually come from the parent star, and for us, that star is sun. Right, so we know that any element, and that sort of hypothesis was initially given by Arthur Eddington. That is something called the synthesis of elements within the stars, and it was given as early as 1914. But then by 1952, the discovery of strontium, that is technetium-98, a material which is produced entirely by a process called nucleosynthesis within a star. Okay, and that discovery of this element sort of put a gave credit to the theory of this synthesis of elements, which was initially given by Eddington, and this was the heaviest sort of element. So you can start that starting from hydrogen, the lightest, to the very heavy elements like technetium, which is 98, and then further up, all these elements get synthesized within a star through a process which is called the nucleosynthesis, right? So as a result, I'm just for your information, I'm just giving you a few nucleosynthesis cycles. Say, for instance, when the carbon interacts with helium within a star system, it produces oxygen. When the oxygen interacts with helium, it produces neon. Magnesium, when it interacts with helium, it produces silicon, and so on and so forth, right? And towards the heavier elements, when we look at titanium, when it interacts with helium, it produces chromium. And ultimately, we know that the most important one is the chromium. When it interacts with helium, it produces iron. And like this, within a star, these stellar nucleosynthesis produces everything that we see around us. And as I said, our star is a very average T Tauri kind of star. When it evolves, it will turn into a red giant. So just to tell you that if you look at the periodic table, you can see that the different colors indicate the origin of these materials in different stages of the star. Say, for instance, the pink ones are through cosmic ray fission. The blue ones are which are coming right from the Big Bang fusion in the beginning. The yellow ones which you are seeing are basically synthesized within the explosive stars, where the stars are massive stars which are exploding. And then there are a few where human synthesis is involved, where we know that we are no other stable isotopes are available for them, and these are all radioactive kind of elements. So this is a very, very important thing to remember always, that actually whatever we are made up of that stellar material, right? So as we know, based on this understanding, we know that Sun today as a star has in its core the hydrogen, which is fusing and creating helium, turning into helium. And there is a mass defect. And because of this mass defect, that much of mass is getting converted into energy. If you sort of take a very classical conversion of this mass to energy ratio, you will see that about 4 million tons of this hydrogen is getting converted into energy every second. And that is the energy we are receiving on the Earth. And this has been going on throughout the life of the Sun. While the life of the cosmos is about 13.7 billion years, the Sun is about, as a star, about 4.6 billion years old. And interestingly, today, as we know, so Earth has a fusion center, fusion is going on, and then there are, near the surface, there are convection cycles going on. These large convection cycles produce a solar magnetic field, and these magnetic fields also contribute towards the energetics of the plasma that comes out of the Sun. So Sun, as a star, not just gives radiation from the Sun, but then it also emits energetic particles, right? These energetic particles, majority of it is hydrogen or protons, but then there are other elements also. It's like the ratio is about more than 96-97% that comes as the energetic protons, and rest of it is all the elements, the energetic elements that we see are coming from the Sun. So this is just to give you what is sort of Sun as a star today is providing to us. On Earth, we are receiving every second, as we know, 13.1366 watt per meter square at the top of the atmosphere. That is called the solar constant, or that much energy we are receiving on the Earth. So if you, at any point of time, if you take an integrated picture, we are receiving about 10 to the power of 12 watt of energy from the Sun on Earth. Now, when I'm talking about Sun evolving as a star, right, it is also important to understand when the Sun was evolving, from that proto material to its core getting formed, and then temperature increasing, and the Sun moving into that main sequence I showed in the first slide. Similarly, Earth also was actually parallelly evolving, and Sun and Earth actually are age-wise are not very different. So the age of Earth is also about 4.5 billion years. So essentially, what does it mean? It means that the sun and the Earth both had evolved together. When the sun was evolving, Earth was also evolving, right? And in the evolution of Earth, many things happened. When the Earth evolved, Earth also formed from a part of the same material of which sun is made up of. We call as proto-material. And a part of it came out from the sun and it made the different planets, right? And Earth is one of these planets. And over the years, over these 4.6, 4.5 billion years, many things have happened on Earth. And the most significant and important thing that had occurred on Earth is the appearance of life. And it is sustained. It is sustained till today, as we know, it is going strong. So sun and Earth, as a system, they had evolved over these billions of years. And so the question that has been normally asked, that at what stage on the evolution of Earth, at what stage life had come, right? So as I said, Earth's life is about 4.5 billion years. And the earliest samples that we get, or the common understanding that we have today, is that the life appeared somewhere around 3.5 to 3.8 billion years ago. So it has been about 3.8 billion years. The life had been existing on Earth, as we know, from a single cell elements to, or those molecules to the complex life forms as we know today. And sources could be many. There are, speculations, and there are experiments, and then it's a whole field in itself that how the life initiated. Some people believe that this life is panspermia. It came from outside. It was not on Earth. So some meteor or some asteroid brought it from outside and then implanted it here. But then there are other theories that it was there in that proto-material, and due to the initial lightning conditions of Earth, when the atmosphere started forming, the lightnings were very strong, cloud systems were there, and those lightning, the energy within that sort of produced life form, the complex chains of hydrocarbon chains. And some people believe that the life initiated or started in deep sea surfaces, or the vents in the, or the cracks from where the thermal energy and along with that some potent for life was there, so life sustained. So like that, there are different various possibilities, but the fact that I want to highlight here is life appeared somewhere around 3.5 to 3.8 billion years ago in this Sun-Earth system. And as we know, that it's very interesting that life in its present form, oxygen forms, or oxygen plays a very, very important role in that. And two elements, right? One is oxygen, and then the other one is iron. As I was telling in the beginning, iron occurs on the Earth in the natural form. We cannot make it. It is made only in the nucleosynthesis reactions in the stars. But these two elements play a very important role in the sustenance of life, including humans. If you consider humans, our breathing cycle, it is or the body, the circulation of oxygen, iron plays a very, very important role in it. As you know that we all talk about it, the hemoglobin or the iron content in our blood. So that is actually essential for carrying the oxygen, the circulation of oxygen in the system. So this sort of, I'm giving you that how intricately we are actually, the life that we know has become a component of the overall system, right? It is dependent on, very much dependent on the elements that, that are coming from the stellar materials, and then, the whole. So we are a part of this system. And why I am telling this, it'll become clear in the coming few slides. So the question at this stage I want to once again ask is that, are we so unique in this whole cosmos that Sun is the only star and Earth as its planet has the only conditions, which are able to sustain Earth and the life forms in it? And the question whether the life had always been so fortunate on Earth, it has always been thriving. Were there conditions in the past when the life sort of almost got extinct, or so were not that unique at all? The question is, the answer is yes. Actually, if we look at the life on Earth in the past, you will realize that there have been in the just past 500 million years alone, if you look at it, you will see that there have been 5 major mass extinction events on Earth. Okay, and last 500 million years is a very short time in the evolution of the Earth, which has a lifetime of about 4.4 billion years or 4.5 billion years. So you can imagine that life had only been in the last 500 to say about a little go beyond of that order on Earth, right? And even in that, there have been events which had really led to the extinction of species. And when I say extinction, we see that a particular type of species completely disappearing from the face of the Earth. And these are the different arrows that you see on the screen. These are actually the mass extinction events. And the most of our friends here, I think, will immediately be able to understand the phase Jurassic, right? This phase where a big arrow is being drawn, right? This is the end of that Jurassic era, right? And we know that this was the time when the dinosaurs became extinct, and so much so that all those species that were of that type on the surface of the Earth completely got its elimination was complete. So such a mass extinction had been there on the face of the Earth, but then every time this mass extinction events happened, immediately after that we see that a new type of species had come into existence, and that sort of led to the growth of the life in a new form. And that exactly happened at this Jurassic period also. That is the period when the modern mammalian species got into existence, and then they became more significant, and from then on we have been surviving very well. And you can see that there have been events like Cretaceous tertiary boundary. Some extinction events were there, but they were not very big, as big as Jurassic, where almost 90 to 95% of the living species got extinct. And these, mass extinction events were caused by, we have fossils which give us information about that. So the information is that the very first major mass extinction happened about, as I said, 444 million years ago. That was the time when the Earth had frozen. Most of the Earth got glaciated. means there were a sudden fluctuation in temperature of the earth, and because of this sudden fluctuation in temperature, the earth got frozen, and because of this cold frozen environment, many of the species could not survive. Then came the next phase where this earth came out of this glaciation, but then that was a phase when extreme volcanic activities were taking place on earth. That is about 365 million years ago. When these huge volcanic activities were happening, what was happening is all this CO2, sulfur dioxide came into atmosphere. Because of this, this species, the atmosphere became toxic, and these atmospheres interacted with the oceans, great oceans. They absorbed all that, and oceans became acidic. And because of this enhanced acidification of the oceans, all the species that were living in oceans got extinct. Majority of them got extinct because they could not survive this sort of a acidification event. And then there was another event which was a kind of a mix of a greenhouse warming because of the methane, the enhancement of methane increasing, and methane being a greenhouse gas. So the overall temperature of the earth increased beyond proportions, and that led to another great dying, we call. And that is actually the greatest dying event that have been recorded, and so on and so forth. And the latest, as I said, Jurassic one, which was about 60 million years ago, 60 to 70. It's believed that it is due to the impact of an asteroid coming onto Earth. And because of that, the conditions became, the light got shadowed because of the dust and clouds, and then the greenhouse, and then, the atmosphere changed, and the species could not adjust to that, and species became extinct. So under this condition, the question is, whenever these major events were happening on the earth, there were some other invisible factors which were playing a role. Okay, and that is what I intended to present to you today. Okay, so if you again take a look at the top one, are those arrows the same curve that I have shown in the previous one, where the 5 major mass extinction events of last 500 million years. And below you are seeing, what is plotted is the Earth's magnetic field. Okay, Earth's magnetic field as inferred using fossils. Okay, I'll be coming to that in a while. And these two plots, and you see along with that, there is another one which indicates oxygen levels, right? So what you're seeing in the bottom two curves, are the variation of Earth's magnetic field in the last 500 million years, and the variation in the oxygen levels in the last 500 years. And I think you all will be surprised by seeing the correlation between the extinction events and the fluctuations in the magnetic field and the oxygen levels, right? And this has been the very latest discovery. As early as now 2015, this sort of correlations were found in from the rock and minerals. And it is really intriguing. What it shows is the variation of oxygen levels on Earth was varying more or less the similar way as the Earth's magnetic field was changing. And not only that, it also shows that the Earth's magnetic field had been continuously changing over last 500 million years, right? And this is not what we understand today. Like our atmosphere, we know that our atmosphere, a majority is nitrogen, this much percent is oxygen, and it is fixed. That ratio is fixed. right? For last so many hundreds of years, if we consider that atmosphere is not variable. So this is really intriguing, that how is it, or what is it that is controlling these three things: extinction or the major changes in the life forms versus the magnetic field variations on the earth and the oxygen levels on the earth. And this is amazing correlations have been found scientifically using different materials. And the question that you may ask, especially to our young colleagues, they may ask that, okay, how do we know the magnetic field, say 500 million years or 2 billion years earlier, right? So we have now some magnetometers which are made up of superconducting materials, right? So that is called a superconducting quantum interference device called SQUID magnetometers. These magnetometers have a very unique property, right? In your physics classes, you would have read that these permanent magnets. These permanent magnets are permanent because, like magnetites and things like that, or iron, for instance, have this magnetic field because the molecules or their dipole orientations are in a particular way, right? There are domains within the material. All these domains are directed in a particular way, and that is leading to this magnetic field, permanent magnetic field in it. So what this SQUID magnetometer does, because of its superconducting coils, that it can record if we can find out a crystal or a rock sample, a very, very small rock sample, say for instance zircon, and if we can take a section of a zircon crystal, and if there is only one such magnetic domain surviving within crystal, right, we can put this domain into the SQUID magnetometer, and we will be able to measure the magnetic field, which is as low as 10 to the power of minus 24 Tesla. So you can imagine the kind of sensitivity the magnetometers, the modern magnetometers have. Okay, and because of that, we can tell that, okay, that was the time, this age, this was the magnetic field, right? And that is how we know. And so if we plot now the magnetic field based on the SQUID magnetometer measurements, if we plot for last 4.2 billion years of Earth, you will see that the magnetic field records show that in the beginning of the Earth, say around 4.2 billion years, the magnetic fields were larger. In fact, their values were large. And then from 4 billion years to about 3 or 3.2 billion years, the magnetic field continuously decreased. And after that, again, the magnetic field showed some sort of a enhancement. And you remember 3.2 to 3.4, I said, is the time when the life on the Earth, it's believed that life on the Earth started, correct? So there seems to be some connection between this magnetic field variation and the time the life appeared on the Earth. We can still go further. If we plot the whole duration, right, whatever samples, geological sample we get from different continents, people have analyzed them. And then one very interesting fact we see. In the beginning of the Earth, we see that the magnetic field values are very low, right? Very low values. And then suddenly the magnetic field enhances. It reaches a maximum, okay? It increases, and then for a very long period of time, that is from 3.5 billion years to about 500 million years, okay? The magnetic field continuously decreased, right? This is a very, very interesting fact. And then around 500 million years, the magnetic field from then on enhanced. And till today, we are seeing that this magnetic field is more and it is increasing. All the samples show an enhancement in this period. So this is a very, very interesting fact or interesting sample that or understanding that have been received recently. So it has been explained based on the fact that, it is believed that when the Earth started, as I said, it started from that proto material of the sun. So it with the gravity, with the gravitational pull, it sort of its core temperature increased. So in the beginning, when the temperatures were low, the magnetic field values were magnetic field was non-existent or low. And then as the gravity enhanced and the core temperature increased, the magnetic field, some sort of a convection activity started in the center and the magnetic field enhanced. But then it could enhance only for a brief period, for say 500 million years or so. And then after that, it sort of continuously decreased. So what does it mean? It means that in the initial stages, when the gravitational collapse happened and then the core temperature increased, our core dynamo did not set up immediately. It actually initially, because of the temperature, this temperature gradient sort of maintained this magnetic field and the convection for a very long period of time, till the magnetic field almost became zero, where the thermally driven dynamo was kind of becoming non-existent because of the temperature, decreasing temperature. And there something happened, and because of that, that geodynamo action started again, and the magnetic field again picked up, and it went as high as it is today. And if we see this in complete period, so from 4.5 billion years to today, zero in the middle panel, you see that our magnetic field had been varying the way we said, and at different stages of these magnetic field perturbations on the Earth, we had different life forms coming and then changing. So we had, say, about multicellular eukaryotes appearing somewhere around 1500 million years. And then the great oxidation event, I'll come to that, happened somewhere about 200 or 2.5 billion years ago. And the middle panel is clearly showing you that how the magnetic field had been continuously varying, and with each variation of the magnetic field, there is a change in the oxygenation and the life form on the Earth. So this fact now has become, uncontested, that magnetic field and the oxygenation of the Earth happened at the same time, has played a role in the sustenance of the life. And the magnetic field is what? Magnetic field is nothing but the material, like the iron-like material playing a role in the convection in the geodynamo. And oxygenation is sort of needed in the mammalian life form, or almost all kinds of life forms. So it is believed, that somewhere around 500 billion years, 500 million years ago, that is the period when I said the modern, those 5 major extinctions of life happened. That is the time, the beginning of that is the time when the geodynamo also started, right? And it is believed that this geodynamo was started due to the interaction of a foreign body. Actually, it is believed now that when the thermally driven dynamo was collapsing, that was the time when an asteroid kind of object, a big asteroid kind of object, impacted on Earth. And the impact was so dramatic that it cracked the surface of the earth, right? And cracking of the surface of earth, you know, is in modern scientific term known as the tectonics, the plate tectonics of earth. Earth is the only planet, you know, when we compare earth with Mars or Venus, we know that earth has a very active tectonic activity, right? That is the one which leads to volcanoes, and that is the one which leads to earthquakes. But that is the one which also oxygenated the atmosphere. So what happened was, all that material which was absorbed on the ocean, in the ocean, and on the material below the surface, when the impact happened, that was pushed into the core of the proto material of the earth, and that sort of triggered this geodynamo activity. And that geodynamo activity, once it got triggered and got self-sustained, it started creating the magnetic field, Earth's magnetic field as we know today, right? And Earth became a sort of a dipolar sort of natural shield around the Earth. And so now it's very, very interesting to sort of put everything in the context. So around 4.6 billion years, Earth came into existence, and then our dynamo activity started somewhere around 3.5 billion. But in the beginning, it was thermally driven. 3.8 around that time, our first records of our first life forms started appearing, and then came the oxygenation of the atmosphere. That is the time when the magnetic field became the major oxygenation happened. Then so now you can imagine till 2000 to about 500 million years, and then comes this yellow box, and that is the one which is called the modern oxygen level. And that is the level where the complex life forms started emerging. And then you can say that immediately after that, we had complex life forms coming into picture. Then we had 420 million years ago, we have fossil records of plants and things like that. And then about 2 million years ago, we had humans already walking on Earth. So it's a fantastic sort of, the combination of factors which led to the occurrence of life on Earth, and then how it was preserved. So just to give you a sort of a feel or encapsulate what we have discussed. So that before the great oxygenation event, the first point, the atmosphere contained high levels of methane. And, when the oxygen started accumulating after the impact, the methane interacted with oxygen. And when these two interact, the carbon dioxide and water start forming. So it means that was the time when CO2 and water came because of the combination of the enhanced oxygen level in the atmosphere. Once the oxygen levels of in the atmosphere started increasing, this oxygen levels also in the presence of UV radiation and nitric oxide and things like that started forming ozone layer, right? Ozone molecules. Ozone is O3, right? So O3, the uniqueness, you all know, the ozone is the layer in the atmosphere of the Earth which absorbs all the harmful ultraviolet radiation, right? It stops this radiation high above. It doesn't allow it to come down to the biological life forms. Then the ocean chemistry also got oxygenated. And because of this, the oxidation of the iron, which was dissolved in the water, it got oxidized. It came out from those oceans. and then it is deposited on the land masses as iron ore, and that is what we find in different places. And that's how we detect the magnetism on the earth, that what happened at what time, right? And oxygenation also sort of reshaped many of the cycles, like carbon, sulfur, nitrogen, and the overall level of through the scattering of the atmosphere, right? The solar radiation by the atmospheric molecules. It also kind of regulated the atmospheric temperature to the levels where the life forms were able to sustain. So now it's very interesting to see that we have a combination of Earth's magnetic field and the atmosphere, the oxygenated atmosphere, which has ozone layer, which is protecting us from the ultraviolet radiation, while the magnetic field is protecting us from the high energy radiation, which is coming from sun or the other stellar objects. So these two, magnetic field and the atmosphere on the Earth, right, they have played over the millions of years, they have played the role of protecting this life form, not just protecting, but they became, in a way, the sustenance, the major factor for the sustenance of life. So that's what I wanted, when I said the guardians of life. So these two, in my opinion, are actually the guardians of life in this Sun-Earth system. If if one asks me, what are the two factors that have led to the sustenance of life over these millions of years? In my opinion, undoubtedly, it will be these two things: the atmosphere, which is oxygenated, and the magnetic field of the Earth, which had stopped all the harmful radiation, which is particle radiation, high energy radiation, which is coming from the sun. And today, as we know, the Earth's magnetic field, it's very interesting. See, sun, you are seeing on the left side of the, so as a star, sun is big, and sometimes it can throw out a very high energetic mass, right? Plasma. So this plasma can come out of the sun, and it is hurled towards Earth, other planets, right? So it can come to Earth, Venus, Mars, it can go to Jupiter, it can go farther than Saturn also. And the energy content of these coronal mass ejections are so much that their size itself can sometimes be much bigger than, many times bigger than the size of the Earth. Okay, but the most interesting fact about Earth is Earth's magnetic field, the field that I've showed you around, the field which is generated in its core, it protects the Earth and its atmosphere. So you see, Earth is at the core, right, at the center, and all these blue lines that you see, these are the magnetic fields, right? And anything which is coming from the sunward side, it is not able to directly penetrate these magnetic field lines to reach Earth, right? So this distance, this RS, whatever I'm showing, this distance is called the standoff distance, right? So this standoff distance is almost right now is about, depending on the energy of the solar wind, it can be somewhere around 10 times the radius of the Earth. Okay, so it's quite far. So anything that is coming from the sun, anything energetic, it cannot come directly to Earth. So our magnetic field protects it. Okay, and the atmosphere, we know that our atmosphere is shielding all the energetic radiation that is coming, the X-ray, the ultraviolet radiation, and extreme ultraviolet radiation. All those radiation in the atmosphere gets absorbed higher in the atmosphere, somewhere around 100 kilometers and beyond. So you can imagine sun and earth and the life in it has evolved in such a beautiful way that the magnetic field protects us against these high energy particles. Atmosphere is protecting us from the ultraviolet radiation, extreme ultraviolet radiation, X-rays, and all these harmful radiations. And the oxygen of the atmosphere is giving us the energy that is necessary for our sustenance on the earth. So it appears that our evolution on earth, and ozone is so important, right? Ozone, if ozone was not there, as we know that the global it will be, all these major harmful radiations will be reaching earth. So the point is, because of these combination of these factors, sun-earth system has become such a beautiful system for the sustenance of life that it serves as a scale, a universal scale for finding out these exoplanets, right? Whatever I was telling that, say today when we say, mostly this is towards the young students. So they hear that one exoplanet was found and another Earth-like planet was found so many distance light years away and near this star. How do they really know this, right? So that is done based on our understanding of the sun-earth system, right? If we take the sun and the earth or the sun and its planets as the standard, the distance of the sun from the earth serves as the region where the life is found, right? This is what we know from our experience. So it means for a sun-like star, the distance of earth, if that much distance some planet is there, then mostly that planet has conditions in it which are life-sustaining. Now you translate that information to a star, let's say, which is not like sun, but that is 10 times heavier than the sun, 10 times bigger, right? So what will happen is the similar conditions will form at a much farther distance from the sun, from that heavier star, right? So if you extend this green zone, you will see that, it will be forming somewhere 10 AU away from the parent star. And that is how, when the astronomers look at the sky, they first look at the objects which are like sun-like stars or heavier than sun or lighter than sun. And then they see their planetary system, right? And then they look for a planet which should be at a distance which is analogous to the sun-earth distance. And that most probably is assumed to be the place where the probable life is existing, and that is why this is called the famous Goldilocks zone. And that's how our quest for the Earth-like planets continues. Okay, and last, before I close my talk, we have now this zero indicates the present time, right? And the present time, we know that we are the major life forms, right? The mammalian life form, the humans are the ones, okay? So this is called the Anthropocene era. But then this is also a fact that even though the humans are surviving, or humans are actually surviving, and then we are abundant on the earth, but then many other life forms are becoming extinct in the present time also, right? So are there indications that in the present time also some change in the magnetic field happening, or the change in the oxygenation of the atmosphere is happening? While we don't have a direct measure of the change in oxygenation of the atmosphere, but then importantly, we are getting indications that our magnetic field of the earth is definitely undergoing a major change. I think you would have come across reports where it is mentioned that the earth's magnetic field is decreasing, and over the poles, the North Pole is moving from Canadian region to Siberia, right? It has shifted, and the South Atlantic anomaly, there is a place in the South Atlantic Ocean, over the South Atlantic Ocean, where the Earth's magnetic field is rather weaker, and this is a well-known anomaly. And it is found that in recent years, the extent of this anomaly over the globe is extending. It is expanding. So what it means is the magnetic field is definitely undergoing a change. The magnetic field is decreasing, right? So if the magnetic field is decreasing, then what is it that we expect? What kind of effects we can expect, right? So presently the situation is, if this is Earth, so you know that all those blue lines are the magnetic field lines coming from the north side of the Earth, and the yellow ones are the south side of the Earth. So this is the ideal dipolar magnetic field, right? But then if the magnetic field is making a reversal or magnetic field is undergoing a change, then what we are expecting is a situation which is shown in the right. Okay, so we have magnetic field becoming weaker. Those anomaly regions are increasing, right? So those magnetic anomalies on the surface of the Earth are increasing, and it can be the magnetic field, when the magnetic field reversal is taking place, the location of the pole, right, it can shift towards countries like India, which is a tropical country. Okay, so the net result is the processes or the features earlier people were seeing in the polar regions, that can happen over the equatorial or the tropical countries. And in recent years, we are seeing that more and more geomagnetic during when the sun is active, we are seeing this auroral sort of illumination in the low latitude regions in the countries, or in the latitudes which are closer to countries like India. So there are definite indications that the magnetic field is making a change, but then we need not worry. Okay, this magnetic field is not going to change within a year or two. We are talking about time scales extending in millions of years, right? So definitely it's not going to happen in yours and my lifetimes. Okay, but then it may or it might eventually happen, and then some other evolutionary pattern or evolutionary cycle may come into existence. We may see a new life form, okay, which could be more adapt in facing the conditions on the Earth. Okay, so with this, I have come to my presentation. So I thank you very much for your attention, and I'll be happy to answer any question. Thank you.
Hello, you have the Q&A question.
Hello, sir. Good
afternoon. Yes.
Okay, sir. So first of all, I would like to thank you for such an engaging and informative class. So even in the peak exam time, there is 50 students in this class, and it really shows how engaging and informative your class was. So, sir, can we move on to Q&A? Sir?
Please. If you have any queries, you please go ahead.
Sir.
Yeah.
So, sir, the first question is from Gautam Krishna of Standard 12th.
Yeah.
His doubt is, we are able to synthesize some metals in the laboratory. So why can't we make iron in the same way?
Right. So that is, some of the materials or some of the elements we can synthesize. Okay, we can make. But then to carry out some of the reactions in order to make them happen, the enthalpy need to be satisfied. I mean, the energy requirements of the reaction need to be met, and that the change in from one element to another in terms of the electronic distribution and things like that, it requires amazing or huge amount of energy, which can only be generated in a reactor, right? In a nuclear reactor. And even in our nuclear reactors, we have a limitation. We cannot go beyond a certain energy, right? Say, for instance, when you might have heard about the Large Hadron Collider, right? The European Large Hadron Collider, where the particle, the fundamental particle and the field studies are being done. So these are the experiments where the two particles are accelerated to MeV energies, and when they collide with one another at a particular point, they give rise to fundamental particles. Okay, so these particles can be pions and all those fundamental levels, even going down to quark thing. But then the energy requirements that are needed for needed to carry out these transitions are huge, and which can only be met in condition in a place like where the nuclear energy is being converted into energy, and which happens only in stars. So that is why it is difficult to do it. But some of the elements it is done, like the radioisotopes, Madame Curie, her experiments and all. So there, some of those isotopes could be made and then could be synthesized in lab, right? But they were not stable again.
Okay, sir. Thank you. So, sir, there is another question from a student named Adil Prajesh.
Yep.
So his question is, can auroras damage our magnetic field and Earth very much?
Actually, auroras are a result of magnetic field. Okay. So what happens is the energetic particles, when they come, they move along these field lines, right? So what magnetic field does is it guides these particles, right? So you can imagine these magnetic field lines as the flux tubes, right, through which these high energy particles can move. Okay, so aurora by itself cannot affect the magnetic field, but then the magnetic field and aurora are very closely linked together. Okay, so if the magnetic field structure is changing, the auroral pattern will also change. Okay, that is the point. And if the magnetic field orientation moves to some other, say, as I said, if it is changing the latitude, it is coming to, say, tropical latitudes, then we will see some of these events happening over these regions, which have never happened earlier, right? So that way, aurora by itself cannot affect the magnetic field, but then it is tightly correlated to, or they are interdependent on each other, you can say.
Okay, sir. Thank you for the informative explanation. So, sir, there is another doubt by Adidev of 9th grade. So his doubt is, in the earlier graph, why does the Earth's magnetic field fluctuate so much in the past 150 million years?
It's a very, very, very good question. The geodynamo in the first, like the way we understand, when the Earth was forming, in the beginning years when the stars form, it is basically, first thing is the gravitational collapse, right? So under the action of the gravity, the accumulation of mass happens, and as more and more mass comes together, the core of the star or the core of the accumulation, there the temperatures start increasing, right? And because of that, some temperature gradient or thermal gradients start appearing within the accumulated or within the accumulation body, right? And so in the initial years of Earth's formation, that is what is believed was happening, right? So the initial part of the magnetic field which appeared, which is recorded, was generated because of the dynamo or because of the thermal dynamo. It was not because of the core, the churning of the core as we know today, right? And as the time elapsed, and because there was no further source of energy, this core temperature started decreasing slowly. And as a result, the magnetic field also started decreasing, correct? But then later on, when we come closer to 500 million years, when the plate tectonics came into picture, the plate material, actually tectonics, or what happens is the surface material goes inside the earth. The mantle goes inside the earth into the core, right? So there is a churning of this material, right? So Earth's, whatever you are seeing on the top of the surface today, it may not be on the surface, say, a million years from now. Okay, it may go down into the mantle somewhere deeper. Okay, interacting with the geodynamo, right? And then resurface again. So this sort of a churning is happening in the case of modern geodynamo, where the plane, where the tectonics is active. Correct. So that is why on the Earth still you see, these earthquakes happening, there's volcanoes happening, and then tsunami came because of the shift in the level of the ocean surface, right? So all this is happening, and this churning gives rise to changes in the magnetic field also, right? So that is the reason that modern times we see more fluctuations, more changes in the magnetic field, while in the past it happened over billions of years.
Thank you, sir, for this great explanation. So next we have a doubt from Samrat Singh. So if he is here, he can ask the doubt directly to sir. Is Samrat Singh here? Okay. If not, sir, his doubt is, does Earth's magnetic field goes through a cycle across billions of years?
Oh yeah, definitely. Earth's magnetic field undergoes a cycle. There is a very famous cycle which is known as the 11-year cycle. Okay, it is the which is related to the changes on the sun. So sun shows magnetic field changes at every 11 years, right? And when it comes to Earth, the Earth's magnetic field variation cycles are over millions of years. Okay, so our periodicity, Earth's magnetic field change periodicity is, I think, if I remember correctly, somewhere around 11 million year or something like that. And there is another periodicity which is of the order of 10,000 years. Okay, so the orientation of the magnetic field changes every 10,000 or so years when the polarity changes and things like that. So that is, so definitely the Earth's magnetic field has cycles of polarity also, other than random changes. These polarity cycle changes also are there, which are periodic in nature.
Okay, sir. Thank you. So there is another doubt by Adil Prajesh. So if Adil is here, Adil can ask the doubt directly to sir.
Hello, sir.
Yes, sir.
My question is, the ocean creatures like sharks, whales, and etc. They are so huge than the land animals.
Yes.
Is this related to gravity?
Is
this related to gravity?
Oh, their shape and weight and things like that?
Yes.
I don't think so, because their evolution is, because their evolution had been in the ocean. Okay. And if you see the oceans, no, ocean is something like our space, right? So if you go down the surface of the ocean, okay, so the radiation beyond a certain point, the radiation doesn't penetrate, correct? So your sunlight doesn't go there, and the temperatures are extremely low, okay, and your availability of the necessary minerals for surviving also becomes low, okay. And so all these factors lead to some sort of evolutionary control for the species. If they need to survive, they need to have this mechanism of countering the decrease in the solar radiation, less amount of the necessary minerals, and like that. So some of these species, you will see that they have this capability of moving to very long distances, right? In order to survive, what they do is they follow the currents in the oceans. The oceans, they have the are there. A lot of food materials are there. Correct. So the major species like whales and sharks and many such species, they are known to follow these currents and move along these currents for very long distance in the oceans, international oceans, to replenish themselves. Okay, and I think that is the reason that their bodies are so big, and so it's a part of the evolution. And gravity, I think, might not have been a factor alone for them, because gravity would have been the same for all the species that were evolving around the same time. Correct? All these species would have felt the same sort of gravitational force. Correct? So I feel it would have been the other major players more influencing that rather than gravity. But that's my view. Okay, gravity, I may have to find out whether gravity had some role to play. Okay, but as of now, my feeling is no. Okay.
Okay.
Good afternoon, sir.
Yes, please.
My name is Sangavi. I'm studying in 9th standard.
Okay.
First of all, I'm thanking to Tarun sir for taking us a wonderful class, and I also thank to VSSC because I got an opportunity to become a part of interaction with Shubhamshu Shukla sir held on July 3rd in Trivandrum.
I see.
So I came there. And I spoke there in the occasion.
Very nice.
So I'm very happy. And
were you a part of Yuvika? You were a part of Yuvika?
Yes, sir.
Ah, okay. Right.
Sir, my doubt is a simple doubt.
Yes, please.
That our sir, you said that there is a change in the magnetic field.
Yes.
When the life starts on Earth, what is the reason, sir?
Actually, that was the time when we said that the modern life form started, was the time when the geodynamo also started into or came into existence. So the magnetic field had almost turned down to zero just before the burst in life. When the life form came, the magnetic field was almost approaching zero when the geodynamo became active because of the plate tectonics, and then probably the impact of some asteroid. Okay, so that is how the magnetic field had sort of suddenly picked up from there, and that also led to the oxygenation of the atmosphere. So this oxygenation started influencing the life form that we were seeing, and then the further evolution of species, and the magnetic field also kept on growing and undergoing changes from then on.
Srikala,
Yes, sir.
you were invited to VSSC for having a talk with Shubhanshu Shukla, isn't it? That was, the thing which I know about it, and I had met you also after that. But you are never a part of Yuvika, isn't it?
Hello, sir.
Yeah.
Hello? Were
Yes,
you a
sir.
part of Yuvika? Could you get that ISRO's Yuvika thing?
Hello, sir.
Okay, we'll carry on. Ritvik, I understand.
Yes.
I understand. Shreya and Rishika have raised some questions, I believe.
Okay.
Oh,
Yes,
sir,
sir.
I was going on the order. So should
Okay,
I
please do so. Please go ahead. Don't go by what I am
Hello,
saying.
sir.
Please go by your order.
Sir, hello, sir.
Yeah,
Can you hear me?
yeah, I can.
Okay, sir.
Yeah, we can hear you. Yes.
Sir, I can't hear that what E.K. Kuti sir asked me.
There is a program of what our respected speaker asked you. Were you a part of Yuvika? There is a scheme of ISRO where the students are selected at the 9th standard level, and they are given an opportunity to spend about a month in ISRO itself.
Yeah.
Were you a part of that scheme? That was the question asked.
Oh, sorry, sir. I didn't hear that question.
Okay. Yeah.
Sir,
No, we had 4 students in the last 4 years or 5 years who got into each year got into
Okay.
the Yuvika scheme
Great.
in our group, this group itself.
Okay.
But I don't know if any of them
Yeah.
is present today. But I don't think Srikala was one among them.
Okay. Yeah, because I had been associated with the Yuvika for last 4 years, I think.
Yeah, you must have been taking them along and all.
Yeah, that's right. So that's why I suddenly felt probably maybe she was a part of that.
Okay, Ritu, carry on. Sorry for interfering.
No issues, sir. Okay, sir. So there is another doubt by Adidev of 9th grade. So if Adidev is here, he can ask the doubt directly to sir. Hello. Is Adidev here?
Adidev.
His mic is not working, he says.
Okay.
Yeah.
So, sir, the doubt is, recently, biosignatures of iron sulfide and iron phosphate were discovered on Mars by the Perseverance rover. Is there any explanation to these compounds occurring naturally on Mars instead of having been made by past biological life?
That's exactly. That's actually, this is the very recent discovery by the Perseverance. And now it's being debated whether these sulfides that have been seen, whether they are formed by the biological life forms, or they are part of some other chemical reactions, because they can be created by chemical reactions also. Okay. So right now, I think it is not very clear, or it is well established that it is definitely a biosignature, because it is, I think this has come very recently, probably in last 10-15 days only. I think I read about this discovery. Okay, so I think it's still being debated.
Okay, sir. Thank you. So, sir, there is another doubt by Shankar of class 9th. So, if Shankar is here, he can ask the doubt directly.
Hello, sir.
Hello, Shankar.
Sir, what would be the consequences of a planet with twice the magnetic field strength and oxygenation of Earth, assuming it stays in the same position as Earth in the solar system?
Very good question. One thing is the when the oxygen level goes up, no, the oxygen is not only a preserver of life, but then too much of oxygen, if it is there, then it leads to oxidation of species, right? So oxidation, when I say what I mean is things. It helps in things in disintegrating or burning. Correct. So especially the chemical compounds which are reactive to oxygen. Oxygen, as it is, becomes reactive when too much of oxygen is there. Then most of this oxygen-governed chemistry would become dominant, and it may happen that some of the molecules which are needed for sustenance of life may get affected adversely. Okay, so so life form, when it comes to I'm talking from the point of view of biology, right? So similarly, like for humans, if we are left in no pure oxygen environment, 100% oxygen environment, we will not be able to survive for long. Okay, because then, as I said, many molecules which are there, which are needed for our chemistry going, they start interacting with this excess oxygen, and which is detrimental. Okay, so this is for oxygen. But then when it comes to magnetic field, if the magnetic field is doubled, okay, the strength is doubled. So what will happen is the standoff distance, as I was telling, right, the protection distance of Earth, that will also become more. So the magnetic field, enhanced magnetic field, it will provide better protection for the planet against the incoming charge particles. Right? So we will have a better protection, magnetic field protection for Earth. But then the enhanced oxygen, that could lead to some of the chemistry which is right now, which is not happening. But then that may become active when the oxygen is doubled. Okay. So in my opinion, enhanced magnetic field will definitely be a helpful situation. I mean, it will be helping. If the biological species adapt to that magnetic field quickly. But then increased oxygen levels, there I have my doubt depending on the chemistry.
Thank you, sir.
Okay, sir. Thank you for the informative explanation. So, sir, the next question is from Samrat Singh. His question is about space travel. Is there not any way to reduce time taken for interplanetary travel? Stronger engine, efficient fuel, maybe gravity assist?
Gravity assist we do. We already take into account that when we are sending our Chandrayaan mission and then mission to Mars, even Aditya mission. All these missions, this gravity assist was a factor. Okay, but then when we are talking about distances, like this is only to the next planet, right? But if we are talking about journey to outside our planetary system, right, we need alternate energy sources. Okay, the normal, regular form of energy, with that we may not be able to to fuel such a journey, because we are talking about distances which are light years. Okay, and to counter that, we need to have some next generation technology. Right now, I cannot think of anything which can make it fast even by a nuclear reactor as an energy source. If you carry a nuclear reactor in your spaceship, even that would require a huge amount of resources. Okay, but still the times would be very large. So I cannot think of something which can be employed, right? Unless we have some. No, there are some imaginary or some situations where sci-fi things where the wormholes are being used. Right, they say that one end of the wormhole will be used, and then as you cross over that, you are in another world, right? And there, then you can go to the next galaxy or generation. So with a very few, with a less energy, using the space-time curvature of the cosmos, right? But then this is all sci-fi right now. I'm not sure whether we have any such thing.
Thank you, sir.
Yeah.
Okay, sir. So there is another doubt from Shreya K. Bhatt. So if they can ask the doubt directly to sir. Is Shreya K. Bhatt here? Okay, sir. So the question is, will solar cycle cause any impact on the cosmic radiations? If yes, then how will the cosmic rays adjust this?
Definitely. Solar cycle, actually the magnetic field, essentially the magnetic field shields Earth from the cosmic ray particles, right? These cosmic rays are high energy particles, right? So when the Earth's magnetic field is strong, these cosmic ray particles cannot penetrate the magnetic field and come inside. So it means the protection is better when the magnetic field is stronger. So the 11-year cycle that I was mentioning, the solar cycle. So when the cycle is active, when the magnetic field is strong, the cosmic rays entry into the Earth's atmosphere is less, but when the magnetic field becomes low during that cycle, right, that is the time when some amount of the cosmic ray particles can enter. Okay, so essentially they are anti-correlated, right? So when the Earth's magnetic field is strong, the cosmic ray particle entry is prohibited. When the Earth's magnetic field is low, some part of it can penetrate this magnetic field and enter.
Okay, sir. Thank you. So next we have a doubt by Rishika. So if Rishika is here, she can ask the doubt directly to sir.
Yeah, sure. So, sir, first of all, I have to mention, thank you for such a wonderful session. The energy and the enthusiasm you carry to explain these complex topics to students like us with such ease is truly commendable. So my question goes as, why were auroras observed at latitudes as low as 30 degree to 35 degree north, for instance in Ladakh, during this storm, when normally they stay near the polar regions?
Right. That's a very, very good question. That is what recently we have been seeing, that more and more these geomagnetic storm events are able to produce these auroral activities to latitudes as low as that of Ladakh and Tibet and like that, right? So essentially what it means is that the magnetic field, overall magnetic field orientation and the magnetic field strength as a whole is decreasing, right? This is saying a climatological sense, okay? But then when we talk about these geomagnetic storms happen over a period of say 10 days, right? Maximum lifetime of that is about 10 days or so, right? So we are not talking about a change in magnetic field, Earth's magnetic field, from the inherent change in the magnetic field within this 10 days. Okay, what we are talking about is the inherent change in the Earth's magnetic field happening in recent years. Recent years means I'm talking about hundreds and thousands of years. Okay, and because of this, all these storms that are happening nowadays in recent we are seeing it for last maybe a couple of years. The major geomagnetic storms, all major geomagnetic storms are creating these auroras to lower and lower latitudes. So that is the connection. I mean, that is where we say that probably the magnetic field, as we know, is decreasing. And because of that, the particles are able to penetrate to lower latitudes. Okay. And that is why we are seeing auroras over these locations. But I think it will become more and more when the sufficient statistics is developed. Then I think we can be sure about this fact that yes, it is definitely because of the change in the magnetic field that these auroras are coming over to low latitudes. And then we will be able to also say that, you know, this is the direction the magnetic field is going to change. Yeah.
Okay, thank you, sir. Can I ask an additional question if
please.
You don't mind?
Yeah, most welcome.
So my question is, why did the thermosphere experience like overcooling, that is density depletion, after the main phase of the storm, even though solar EUV input remained high? What processes caused this delayed cooling effect?
It is actually the cooling that you are talking about. It all depends on how much of energy during a geomagnetic storm has been deposited into that thermosphere, ionosphere region. Okay, and because the temperature in thermosphere is the temperature that is a kinetic temperature, right? Which is actually which reflects as a local, when many species come under local thermal equilibrium, and that is the temperature we say that, okay, that is the kinetic temperature of that region. So what happens is when during a geomagnetic storm time, some of these species, their concentration can get depleted, can get affected. So because of that, the population can go down. Right, the density can go down. So if the density is going down, so what happens is the energy that is carried, the energy density that is carried in that region of the thermosphere, that also becomes less. Okay, and that appears as a change in the thermospheric temperatures. And but then, as you say, it is not always that we see cooling in thermosphere. Sometimes we see heating in thermosphere. Sometimes we see wave-like oscillations in thermosphere. So thermosphere can experience a whole range of changes in temperature, density, and wind, and even ionospheric densities. So and they can be all sort of changes. So, but what cooling that you mentioned, that is primarily, that is the reason for that.
Thank you for addressing with such clarity, sir.
Most welcome.
Thank
There's
you,
a question from Aparna. Aparna had raised her hand for quite some time.
If Aparna is here, she can ask the doubt directly to sir. So is Aparna here? If you are having any mic problems, you can post the question in the chat box. Okay, sir. So there is another doubt by Devik A. Kumar. So if he's there, he can ask the doubt directly to sir.
Good afternoon, sir.
Good afternoon.
First of all, thank you for this wonderful and informative class. So my question is that does solar flares affect Earth's temperature?
Earth's surface temperature, you mean?
Yeah.
Flares don't affect directly, don't affect the surface temperature.
Okay, sir.
The solar flares mostly because right now our magnetic field, as I said, magnetic field acts as a shield. So most of the flare energy goes to these magnetosphere or magnetic field. Okay, and a part of that only appears into the atmosphere, and there too, most of it in the altitudes above 100 kilometers.
Okay, sir. Thank you.
Yes.
Thank you, sir. So that was the last question. I hope everyone has cleared their doubts. And I would once again like to thank you, sir, for such a great class and also clearing all our doubts with such a clarity. So thank you, sir.
Ritvik, we have, I think, amongst us some of the ISRO scientists also, I think, that was there with us. The CBS, that was Dr. CBS.
I'm seeing one hand by Anisa.
Anisa Madari, yeah, Anisa Madari. Okay.
Sir,
You can ask the doubt.
Sir, my name is Fatima Rasha. I'm studying in 8th standard.
Okay.
Thanks for the wonderful class. I couldn't get the class in full because I had a class. But from the questions somebody asked about time traveling, if we make a machine that could travel faster than time, won't we be able to do time travel?
That's precisely. I was also telling that the time travel theoretically, if you like physics wise, I mean, if you take the physics of the time travel, it is there is nothing wrong in the physics of time travel. It is possible. It can be done. Okay, but the problem is technology, right? We right now we don't know how it can be done. Okay, so that is where the catch is. Okay.
Sir, there are rumors about people time traveling to past and people claiming that time is not a straight line but a loop.
Yeah.
Is that right? That time is a loop?
Actually, time is related to time is like space. No, normally what we do is we take time as an independent parameter. Okay, but if we believe in what the Big Bang said, if the space-time curvature is the one which is shaping up this universe, then time is only a dependent parameter like space. Okay, so it cannot be independent. So definitely time can be, that's why I said it can go back, it can go forward. So there can be minus time, plus time, like space. Okay, so that is how we say that in the physics of time travel, it's not wrong. I mean, it is physics wise, it is feasible, right? But it is technology that we don't know how to do it, right?
So, if we make the technology that could do so, we will be able to time travel.
Yes.
But there
I
are
think
people.
if you, there was a movie sometime back, a few years back.
Is it called Lucy?
No, it was in that actually. It was actually the person had traveled back in time. Gravity or something. I think the name was Gravity. Or Interstellar. I think Interstellar probably. Yes.
Adideva
Yes,
said it's
yes,
Interstellar.
yes.
Okay.
Yes. I think it was
Interstellar
Interstellar.
or Event Horizon.
Yes. Correct. So, so if you look at that, so there also it's the curvature of space-time and the time travel is possible because of this space-time orientation. And there you can do it. If technology is there, it can be done. Yes.
Sir, there are people who claims that they have time traveled. What about that?
That I doubt.
Like they
Because there are
have
no different
taken a
definite.
picture from the current year and they time travel to the past and taken a picture from there as a proof.
But
I
I
always
don't.
wondered
Yeah.
about that.
Yes. I understand what you're asking, but I don't think there are very many strong evidences of people actually, who have time traveled and shared information and whose credibility is established. Or
Sir,
at least
if we
I'm not
make
aware.
I think we can stop here. These are a lot of stories and things like that. As Dr. Tarun has said, it has to be evidence based.
Yeah.
Science has to be evidence based.
Yeah.
So let us not. Already we have taken 2 precious hours of Dr. Tarun. Before we conclude, with the permission of Ritvik, I think we can ask our very senior 2 people are there. Dr. Sundaramurthy. TK Sundaramurthy, are you there? He's ISRO Satellite Center, one of the old colleagues.
Oh, I see.
He
Yes, sir.
usually comes. He
Yes,
was
sir.
there. Please.
Yeah.
Well,
I think
your
the
comments, please.
talk was really wonderful, sir. It has given a good insight into the things. In fact, it is a good educative tool for me too. Today I really felt I'm a real student. So
Thank
you
you,
have
sir.
given the valuable information and about all those things. But 1 or 2 things I was from the answers what you have given is about the this whales thing and then its gravity effects and all.
Yeah.
To that extent, that evolution probably will it be similar to again that hippopotamus and other animals what they are having, that I'm talking about the sea based things. But do you mean to say that that could be due to the gene effects or it could be the evolution?
Right. Actually, some of the things like, say, for instance, rhinos, no? You actually brought in a very good point that it is believed that there was during the evolution of life, when the sun was also undergoing a very rapid change, there was a phase when the UV and X-ray doses of radiation were very high on Earth. Okay, even though magnetic field was protecting to some extent, but then these doses were very high. And these some of these species, they adapted through mutations in their genes. They adapted to this change in dosage of radiation in X-ray and UV. And so some of these species, they develop these very thick cover in their exterior body, which can protect them from such radiations also.
Okay.
Yeah. So,
okay, sir.
So some of this is related to that phase of thing. But as you rightly said, it's I think much more complex than what meets the eye.
And my second question is then regarding the time period of that variation of the magnetic fields you are talking about. That is how that got that evolution process how that has come. I'm a novice to this, but interested to know how that is been evolved.
Actually, what now the picture that is emerging is that as we saw that, you know, the Earth's atmosphere right from the beginning, if you look at it, it had been continuously evolving, right? And with each evolution, the species, the major species that play the role in the atmosphere, that also had been undergoing a change. So what people have seen is now that ever since the geodynamo became active, after that the oxygenation of the major event that had come into play from the ancient atmosphere to modern atmosphere is the major oxygenation of the atmosphere, which is due to the tectonic activity, because tectonic activity is the one which had led to the generation of magnetic field at one hand, and on the other hand it had led to the oxygenation of the atmosphere through the subduction of the surface layer into interior core, and then from the core bringing the core material and releasing it into the atmosphere.
Okay.
So that is how then both of them got correlated to one another, sort of dictated by one another.
Okay. Okay, sir. Okay, sir.
Yeah.
Thank you so much, sir, for the rather wonderful lecture. Once again, I would like to thank, I think the students are also very much benefited. Okay. Thank you once again, sir.
Thank you, sir. Thank you.
Thank
you so much.
Thank you, Sundaramurthy. Thank you very much. And Sundaramurthy is one of the key figures of ISRO satellites, your satellite center on mission planning, orbit determination, and flight dynamics and things like that. He's a key figure. Now, Dr. Abdullah sir is there, the teacher's teacher. He is from the district institute of education. Abdullah sir, anything to say? Any comments,
sir?
Any comments, sir?
Nothing, sir. Just I am a little bit late to join with you because I am attending another program in Bangalore. That program is actually I thought to end by 2:30, but it take one more extra hour. That's why little bit late only I could join with your team. But whatever from that point onwards, it was very excellent, very what I can say, very informative and interesting. Even then, all our children are asked the excellent questions, but even opening the further knowledge as well as their enthusiasm is mentioned in each and every questions. So I appreciate the students as well as the sir for giving such an extraordinary delivery regarding this subject. Thank you, one and all.
Thank you, sir.
Thank you, Dr. Abdullah sir. Thank you. Okay, Ritvik, it is handed over to you back. Sorry for intruding into your role. Sorry.
No, sir.
Take over, Ritvik.
All the doubts were already cleared and the questions were over. And I would like to just conclude by saying thank you to sir for such a great session and clearing all our doubts with such clarity, sir. Thank you.
Most welcome.
Do you have any word of thanks kind of thing, Ritvik?
Sir, I am not doing the word of thanks.
Yes, Adarsh will be doing
Oh, no, you're correct. I know somebody will be there. Okay, please come out.
First of all, we're really honored to have you, sir, Tarun, sir, as a speaker. It was an informative session on the Q&A. We're really grateful for that. And a special thank you for P.K. Sundaramurthy sir and Abdul Nasser sir for your insights. And let me move on to the vote of thanks. So, good evening, everyone. On behalf of your speaker, I extend my heartfelt gratitude to each one of you for being a part of our 82nd webinar session. It's been a truly interesting session that took us on a journey into the secrets of our universe. First and foremost, we're really grateful to our distinguished speaker, Dr. Tarun, Tarun Kumar Pant, for his captivating talk. Your extensive expertise in optical and radio remote sensing, space weather, and Sun Earth system development, along with a significant contribution to national space missions such as USAT and Chandrayaan-2, has been a true source of inspiration for the scientific community. We are also deeply grateful to our founder and mentor, Sri E.K. Kuti, whose vision and passion continue to guide and inspire the UL spacecraft to reach new heights. A special thanks to our moderator, Sri Shajil UK, for smoothly coordinating the session and ensuring a seamless flow of ideas and interaction. And of course, a big thank you to all the participants who joined us today. Your enthusiasm, questions, and passion for learning are what make events like this so impactful. With that, we conclude this session. Thank you and have a great evening.
Thank you, others. Thank you. Thank you
Thank
very
you.
much. So
Thank
very
you so
nice of
much.
you, sir. We have taken 2 hours, long hours of your
No
time.
problem,
Precious
sir.
time. Thank you
It
so
was my
much.
pleasure.
And I'm also grateful to your predecessor, Dr. Rajiv,
Rajiv,
for
yes.
introducing me to you. And we never knew each other before that. Of course, we had some occasion, online kind of thing, but not the same. So it's very nice of you, sir. Thank you very much. Let us continue to have interactions in future.
Sure.
For the benefit of these students.
Sure,
Thank you
sir.
very much.
It was pleasure was mine. I really enjoyed the session and interaction with the students. I think this club is doing great, and I am really happy to see the enthusiasm of all the students. And so my best wishes, and thank you to you, sir. You gave me this opportunity to be here. So thank you very much.
It's a great privilege we got, a pleasure also. Thank you very much. So nice. So nice.
Thanks.
So nice. So
Thank
goodbye.
you.
Thank you so much.
Thank you. Thank you so much, sir. Thank you.
Thank you.
Nice. Thank you.
Thank you, sir.